Okay, so we're starting a new module of our course, and it's going to start off from something that you've already seen, 5.1 determinants. So we're starting off on a different module, right? We've talked a lot about rectangular matrices and column spaces, row spaces. That was a bit of an abstract notion that we were talking about. I've also added a couple of videos in the playlist that should help you with an intuitive way of looking at things, or intuitive way of looking at vector spaces. And I think I'll also add another video from Grant Samuelson's channel into the playlist so that you can view his exposition of determinants as well. Okay, and so the way that the determinant that you might have seen the 2x2 determinant, right? So let's say if you have a matrix A, which is a 2x2 matrix. For a 2x2 matrix, let's say these are the entries, then the determinant of A is quite easy to compute, and it's just you multiply these entries and then you subtract the product of these two entries. So it's AD minus BC, right? So for a 2x2 matrix, it's really easy to see that is the determinant. But for a 3x3 matrix, or for a 4x4, or as you increase the number of rows and columns in your matrix, notice that I'm talking about now just square matrices. So we're going to focus on just square matrices. For rectangular matrices, we do not have a notion of determinant, right? So for now, we're restricting ourselves to n by n matrices. For a 2x2 case, this is the formula for the determinant. But if n increases, then that formula, there is a formula, but it's a large, clunky, janky formula that I don't want to get into. Instead, we're going to look at the properties of determinants, and we're going to see how those properties can be used to perhaps simplify the computation of a determinant and make it really easy to compute. Okay, so, and we're going to verify all of those properties with respect to a 2x2 matrix as well, right? So we already have a 2x2 matrix, so we'll just see if those properties translate into a 2x2 matrix. But what is the determinant? The determinant is just a number, right? So it's a number that tells you something about the matrix, tells you something about the matrix. What does it tell us? Well, if you recall from the 2x2 case, the first thing that a determinant tells you is that the determinant of A, if the determinant of a matrix A is 0, then we call it a singular matrix. Singular matrix, right? With a singular matrix is just a matrix that does not have an inverse, so the inverse does not exist. Okay, that's really what we usually use to use a determinant for. It has other applications as well. It can tell you something about the area of a linear transformation, or how does the area change under a linear transformation. It also tells you something about maybe eigenvalues. That's something that will come up soon. But that's really, let's start off from this property. And if the determinant of A is non-zero, then it's a non-singular matrix. Then the matrix is non-singular, which means that the inverse exists. Okay. So what are some properties of the determinant? Let's see. So the first property of the determinant is that the determinant of an identity matrix is equal to 1. That's always going to be true, regardless of, again, the properties that I'm writing down are for any n by n matrix A. And we're going to verify them for just the 2x2 case. In the 2x2 case, you can see if you have just the identity matrix 1, 0, 0, 1, then it's easy to see that the determinant is just 1 times 1 minus 0. 1, 1 minus 0 gives you 1. Okay, so that's the first property. The second property of a determinant is that row exchange. So row exchange changes the sign of the determinant, which means if you have, for example, a permutation, a 2 by 2 permutation matrix, something like this, 0, 1, and 1, 0, all I've done is I've taken the matrix I and I've exchanged the 2 rows of the matrix, and now if I compute the determinant, then we can see that this is 0 by 0, 0 times 0 minus 1 by 1. So that's minus 1. So even in the 2 by 2 case, that also verifies. And you can see it even in the general case, right? So if this is A, B, C, D, and if I then do a row exchange, I do row 1, 2, then this gives me C, D, A, B, and then the determinant of this matrix, so the determinant of, if this is matrix A and this is matrix A prime, then the determinant of A prime is equals to CB, so BC minus AD, which is nothing but, if I take the negative sign common, that's just AD minus BC again. So that's just negative times the determinant of the original matrix. Okay, so the original matrix has AD minus BC, and the row exchange matrix has determinant, the same determinant but with a different sign. So that's the second property. Okay, what else? Third property of a determinant is that it is the determinant is linear in rows. This is important. It's linear in rows. It's not linear. For example, what do we mean when a property is linear? We mean when a property is linear, for example, if you multiply it, if you take a linear combination, this linearity means that the linear combination is preserved. The linear combination is preserved. How do I see that? Well, let's try it out. For example, if I have, let's break it down into 2 parts. So property 3a, first we'll do some scalar multiplication, right? Linear combination involves 2 things, scalar multiplication and addition, right? So for example, if we do the scalar multiplication of a row, then what does it say? It tells us that if I have a matrix T times A, T times B, and CD, so all I've done is, let's use the usual scalars that we used to use, alpha A and alpha B. So all I've done is I've taken alpha times row 1. That's what I've done, right? And this property tells me that the determinant of this matrix, or the determinant, I can also write the determinant by writing, so for example, determinant of A is the same as writing the A in these bars. So if I replace these brackets by these bars, then all I mean is that I'm considering the determinant of this matrix, right? So these bars mean that this is the determinant of this. And the scalar multiplication property tells me that this is the same if you just take out alpha outside and then take the determinant. So A, B, C, D. So this linearity is preserved, that if you factor out the alpha, it won't change the determinant. And perhaps we can check that out. So determinant on the left hand side, we can just verify this for a 2 by 2 matrix. On the left hand side, the determinant will be alpha A times D, alpha AD minus alpha BC. And on the right hand side, the determinant will be, well, alpha is being multiplied. Let's find the determinant of this matrix, which is just AD minus BC, and then that's just alpha AD minus alpha BC. Notice that it's important that it's just in a row, right? Which means if you have something being multiplied with a row, you can factor it out, but you can't do the factorization with the other row as well. For example, if you have alpha A, alpha B, and then alpha C, alpha D, this is not equal to alpha A, B, C, D, right? The reason is because it's linear in each row, which means when you factor out some scalar, you have to factor out it individually from each row, which means what you can do is you can, if you want to make this correct, then what you can do is you can factor out the first alpha from the first row, alpha AB, leave the second row as it is, and then factor out the second alpha from the second row. So this becomes alpha squared A, B, C, D. And you can check that out now that this property is now true. So for example, this alpha A, alpha B, so the determinant on the left hand side is equals to the determinant on this side. So it's not just being multiplied by alpha, it's being multiplied by alpha squared. So this property also tells us, so if I can write this matrix down as alpha times A, right? So if A was A, B, C, D, if A was A, B, C, D, if I multiply alpha with A, then that's just being multiplied with every row, right? Alpha B, alpha C, alpha D. So what we really have over here is that this is the determinant of alpha A, right? So the determinant of alpha A is equals to alpha square for a 2 by 2 case, right? For a 2 by 2 case is that the determinant of something being multiplied by A is alpha squared. I specify that this is a 2 by 2 case because there were 2 rows, which is why there was this alpha squared here. If there were more rows, if we had 3 rows, then it would have been alpha cubed, because then you would have taken out alpha from 3 rows, right? You have factored out 3 alphas. So this gives us another property, which is that I can write this maybe as a sub-property of this one, that is the determinant of alpha times A is equals to alpha to the power n times the determinant of A. What does this say? It means, and this n is, by the way, the dimension of the matrix, which is, if it's a square matrix, it's n by n, 5 by 5, 10 by 10. So depending on that. So for example, if we can see it in 3 rows, for example, if this was alpha A, alpha B, alpha C, alpha D, alpha E, alpha F, alpha G, alpha H, alpha I. If I want to find the determinant of this matrix, this is nothing but alpha times a 3 by 3 matrix, right? A scalar being multiplied, all of them, all of the entries. Now I can factor out the alpha first from the first row, A, B, C, leave the second 2 as it is, second 2 rows, second and the third row as it is, alpha G, alpha H, and alpha I. And then again factor out alpha squared, and then again I'll factor out alpha 3, and A, B, C, D, E, F, G, H, I, right? So that tells me that this is alpha cubed times the determinant of A. Okay. All right. Next up, we have, so for linearity, we have 2 things, right? First, the scalar multiplication, and then the vector addition, right? So let's try addition. And again, addition in a row. That's the important thing, right? So for example, if we have the first row as A, B, C, D, and if something is being added to the first row, so for example, A has A prime being added to it, and B has B prime being added to it, C, D. We're doing a vector addition, right? So for example, I'm adding the row, I'm adding AB to A prime, C prime, right? That's the addition that I'm doing. And this tells us, again, if linearity is preserved in a row, that means that the determinant of AB, CD is the, so the determinant of A plus A prime, this matrix, is equals to the determinant of this plus the second matrix, which can be made, plus the determinant of the second matrix, which can be made by alpha prime, A prime, B prime, CD, right? So notice how this property is preserved. So the idea is that there was an addition happening in a row, which you can transfer the addition to the determinant. So this was now the determinant of this matrix A and the determinant of this matrix A prime. So what has happened is that the addition that was happening inside a row has transferred into the addition of these two determinants, right? But again, this is to emphasize that if I have a different case, for example, A plus A prime, C plus C prime, B plus B prime, and D plus D prime, then that's happening in two different rows. So I can't say that this is true anymore. So I can't say that this is A, B, C, D, determinant of this matrix plus the determinant of A prime, B prime, C prime, D prime. The correct thing in that situation would be to do it again 2 times. So for example, first I can write this as, if I want the correct property, I have to do it individually row by row, right? So I have to do something like A, B, and leave the second row intact, D plus D prime, and then I have A prime, B prime, and then again the second 2 rows will remain unchanged. So C plus C prime, D plus D prime, something like that. And then if you want to separate these 2 rows out further, you can do that, but then you will have 4 determinants instead of 2 determinants, right? So what really this property is telling me that you can transfer the addition as long as it is happening in one row, but it's also telling me that the determinant of A plus B is not the same as determinant of A plus determinant of B. You have to do it row-wise. Okay. All right. Okay, so this preserves the linearity in rows. So if I combine 3A and 3B together, then that tells me what? It tells me the following. So if I have the following, if I have the determinant of A plus TA prime, B plus TB prime, and then CD. So I've done 2 things together now. I've done a scalar multiplication and then I've done addition. So this is equals to the determinant of, I can first separate out the addition that was happening. So row-wise addition is separated, TA prime, TB prime, CD. Let's make that alpha, 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 alpha. And then now I can factor out the alphas from the second matrix. So alpha, A prime, B prime, C, D. Right, so what has happened here is alpha A prime, A plus alpha A prime, B plus alpha B prime. This linearity over here has transferred into this linearity. So something plus alpha times something. This is A plus alpha times A prime. This is the determinant of the whole matrix plus alpha times the determinant of the whole. Right? That's the linearity. Okay, and you can even add a little beta here as well, right? So if I add a beta here and a beta here, so this is beta, beta, and so this becomes this. So again, the whole linearity comes out. Okay, what's next? The next property is the following. If you have property number 4, is that if your matrix has, if A has 2 equal rows, then the determinant of A is equal to 0. We can check that out in the 2 by 2 matrix, right? Let's verify that property if this even holds. A, B, and AB. Let's say these are the 2 equal rows. If I try to find the determinant, it's just AB minus AB equals to 0. And that checks out. Okay. So in a 2 by 2 case, this holds, but it also holds in an n by n case. So for example, if you have a 3 by 3 matrix, right? Let's say the 3 by 3 matrix is something like A, B, C, D, E, F, and then this is A, B, C again. Then I know for sure that the determinant is going to be 0. As long as you have 2 equal rows, then the determinant is 0. And the reason is, another way to see this is as follows. Recall that when 2 rows are equal, then A is not invertible because A has 2 dependent columns with dependent rows and even dependent columns, of course, then the rank is less than the number of rows. So you can really eliminate the whole row and you get an non-invertible matrix, a singular matrix, right? So when two rows are equal, then A is not invertible, which means the determinant has to be 0, right? The determinant of A has to be 0. Because in the start we talked about that invertibility is something that tells us, that is given to us, information about invertibility is given to us by the determinant. So if it's a singular matrix, the determinant has to be 0. So that's the reason. That's another way to look at it. Excuse me. Okay, next property. So property 5 of determinants. Elimination. This is something that we've been doing, when you do Gaussian elimination, you eliminate some variables. But the idea is elimination step. The elimination steps of the form are j minus alpha times ri. This is something that we do, right? We take a product of one row and then subtract it from another row. If we do something like that, then doing the step does not change. Elimination steps do not change the value of the determinant, right? Let's see how this shows up in a 2 by 2 case. For example, let's take a 2 by 2 case. We have 1, 2, and perhaps 4, 6. It should be a non-singular matrix, and let's try to eliminate. Let's try to first find the determinant. So this is A, and the determinant of A is 1 times 6, so that's 6 minus 2 times 4, which is 8. So the determinant is minus 2. Now let's do an elimination step. If we do row 2 minus 4 times row 1, that should eliminate the second entry in the first column. So I get 1 times 2, 1, 2, and then I get 4 minus 4, which is 0, and I get 6 minus 8, which is minus 2. And now let's call this matrix A prime. And what's the determinant of A prime? The determinant of A prime is simply 1 times minus 2. So it's 1 times minus 2 minus 2 times 0, which is 0, so that's again minus 2. So elimination steps. This elimination step did not change the value of the determinant. That's one thing. Notice also that in this lower triangular, this was a lower triangular case, right? So in a lower triangular matrix, when I did AD minus BC, this BC was 0, right? Because when you multiply this with this, it's just going to be 0, which means the determinant is going to be equal to the product. So this was the first pivot, and this was the second pivot. And it turns out that the determinant is also for a triangular matrix. For a triangular matrix, the determinant of, let's say, this upper triangular matrix is just going to be the product of, you can say the product of pivots maybe, or you can say that it's just the product of diagonal entries. Okay, we'll see that in a bit for a general matrix, right? For example, if I take AD, a 2 by 2 case, AB, BC, AB, CD, that's the matrix. If I try to do an elimination on this, then elimination would be something like row 2 minus C over A times row 1. I've taken this fraction, and let's see how that works out. So this is AB, and then this value is going to be C minus C over A times A. So A's will cancel, and I'll just get C minus C, which is 0. And then this entry will be D minus C over A times B. So in this case, if I try to find the determinant, then the determinant of A is going to be equals to, notice that the original matrix of course had the determinant, the usual determinant, which was AD minus BC. And in this case, you can see if I multiply the product, if you multiply the pivots, or if you even apply the formula this times this minus this times this, there is no contribution from B times 0. So the result is something like this. So the result is A times D minus C over A times B. And if you multiply this out, you can see this is just AD minus the A's cancel. You see, so this again exactly the same. So elimination doesn't change your determinant. Let's check it out in a 3x3 case, and let's talk about a triangular n by n matrix, which I mentioned right now. So for example, if you have something like you have some entry here, A1, A2, A3, so on up until AN. These are the entries. And let's suppose this is a triangular matrix, so that every entry over under this, every entry over here, this is all zeros, and there are some entries here, right? Some non-zeros entries there. When I put on stars, which means that they're not zero. So what can I do? I know that I can apply the Gauss-Jordan method, right? The Gauss-Jordan method, that I can eliminate all of these entries, that I can do row elimination in the reverse step to make all of these entries zero as well, right? That's possible if all of them are non-zero, which means I can use elimination steps to convert this matrix into a matrix that has only the diagonal entries. So the matrix can be converted into A1, A2, blah, 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 AN, and all the rest of the entries, all of this is 0, 0, 0, 0, 0. This is all zeros, right? So this is the matrix now. Okay, and I know that elimination will not change the value of the determinant, which means the determinant of both of these matrices is exactly the same. So the determinant of A, this is also, if I find out the determinant of this, then the determinant is still the determinant of A. So this is equal, really. Okay, the matrices are of course not equal, so I can say that if this matrix was A and this was A prime, then the determinant of A was equal to determinant of A prime. Okay. Now what I can do? I can use property 3a, right? What was property 3a? Property 3a told me that I can factor out some, so if I have alpha A, alpha B, I can factor out some multiple from each of the rows. So let's say I factor out, from the first row I'm going to factor out A1. So let's change this matrix into, let's say I factor out A1, and then I'm taking the determinant, and I'm taking the determinant of, if I've taken A1 common from the first row, then the first row becomes 1, 0, 0, all zeros, right? And the rest of the rows remain unchanged. So A2, A3, up until AN. Okay. I can repeat the same process. I can repeat the same process for A2 again. I can factor out A2, and that will make the second row as something like 1 zeros, and then 0, 1, and then all zeros, right? And then give us these. So if you can see what's happening, I'm slowly changing by factoring out each of the diagonal entries. I'm converting this matrix into the identity matrix. So the determinant will then be equals to, so let's just make this into the determinant sign so that it's all consistent. So I was finding the determinant, and so then at the end what I have is, if I factor out all the A's, so A1, A2 up until AN, then at the end I have the determinant of the identity matrix. And I know that the determinant of the identity matrix is just 1. So the determinant is equal to A1 times A2 times A3 times AN. So what does this tell us? It tells us that for any triangular matrix, the determinant is just equals to, I've done it for an upper triangular matrix. You can do the same argument for a lower triangular matrix. Just eliminate all the entries, and what you get is that the determinant, so the determinant of A is equal to A1 if is equals to the product of all the A's of product of all the diagonal entries if A is triangular, right? Okay. All right, so this was property 5, right? And property 5, maybe we can give another name to this property, property 6, that if you have a triangular matrix, then that's just it. And this should immediately tell you, by the way, that the determinant of a diagonal matrix, the determinant of something like A1 to AN is again just going to be equal to, if all of this is already 0, then that's just A1, A2, AN, right? That product, the product of the diagonal entries. So if you have a nicer matrix, then you can compute it. What is this? We can use this property at this point. This is an efficient way to compute the determinant, right? We have a way to calculate the determinant for an n by n matrix. How does this property give me a way? This gives me a way by first, if I have an n by n matrix A, then what I can do is I can do LU factorization and write A is equals to LU, okay? And I have a nice little property, let's say property, what was it? I've reached property 6, right? So let's call this property 7. Property 7 is something that I will write down here, which I'm about to use, is that the determinant of the product of two matrices is equal to the determinant of A times the determinant of B, right? If two matrices are being multiplied, then they have to be squared, just by the way, so that each of their determinants is individually defined. So if two matrices are being multiplied, their determinants are also being multiplied, right? Okay, so this property 7 I'm going to use now, that the determinant of A is just equals to the determinant of LU, which is just equals to the determinant of L times determinant of U, which is by property 8, right? Okay, now notice that when we do LU factorization, the way we've learned it is that in the L matrix, all of the diagonal entries are 1, this is 0, and then these are some non-zero entries. And for U, the entries are some U1, U2, ... And there are some non-zero entries here, and then there is a 0 here, right? Or if you want to make this even more precise, maybe you could do the same thing with LDU. You can try that out later, and you can see how you can compute the determinant if you have the factorization LDU. But over here, I can just note that now, if I'm finding the determinants, right, the determinant of this matrix and the determinant of this matrix, this just has 1s on the diagonal, which means the determinant is just going to be equal to 1. And this has U1s and U2s and all of those on the diagonal, so that I can say that this is U1 times U2 times UN. So that's the determinant of A. That the determinant of A is equals to the product of all the diagonal entries once you find the upper triangular matrix, right? So convert it into an upper triangular matrix, do elimination on it, convert it into this, and then just multiply out all the diagonal entries of the upper triangular matrix, right? Again, I'm not saying that this is determinant of A is not equals to the product of diagonals of A. Product of diagonals of A. That's not true. That's not true because A may not be a triangular matrix, but we know that U, if you factorize A into LU, then U will be a triangular matrix, and then you can just use this. So the determinant of A is U1, U2, UN, or in other words, the product of diagonal entries of its upper triangular factor. Okay. All right. If you convert it into If you factorize A into LDU, then that becomes even more simple. It becomes the determinant of A. You can see that it's just equals to the determinant of D, and that notice that the diagonal entries of D are just these same entries, so it's still just the same thing. Okay, next property. So property 7 also tells us something about the inverse, right? So if the determinant of AB is equals to the determinant of A times the determinant of B, then what about this property? Recall that A times A inverse is equals to the identity matrix, which means the determinant of A times A inverse is just the determinant of the identity matrix because they're both the same matrix, right? But now, since this is a product, I can write this as the determinant of A times the determinant of A inverse. And I know that the identity matrix always has, this is the first property that we did, that the identity just has the inverse of, the determinant equals to 1. Which means if I want the determinant of A inverse, then that's just 1 upon the determinant of A. And you can try it out by finding a matrix and finding its inverse, and you can see that the inverse has the same. It's just the reciprocal of the determinant. So the determinant of A inverse is the reciprocal of the determinant of A. Okay. All right. Property number 8. We've done inverse, we've done this, and okay. Another, I think this is the last property that we'll do, and we'll end the lecture here. So this property tells us that the determinant of the transpose is equals to the determinant of A. So changing the row in the column doesn't do anything. If you have a square matrix, if you take the transpose, taking the transpose, in other words, transposing A does not change the determinant. Let's verify this in a 2 by 2 case. So A, B, C, D. If I then transpose it, so A transpose, this is A, right? A transpose is just, the determinant is going to be, this determinant is AD minus BC, and this is going to be A. The transpose is you make the rows into the column, so AC and BD, but that's just AD again. AD minus CB, which is just, because multiplication is commutative, you can just do AD minus BC. So it's the same, right? And even we can do it even for, we can see that it's for an n by n matrix, we can see that this is true, right? For example, if I want to take the determinant of A transpose, then, and I want to see what the determinant of A is, let's see, these are the two matrices that we're looking at. I can convert both of them. Let's say I factorize A as LU, right? Again, we're going to use the trick that we've learned finally how to compute the matrix. This is the important bit about, I've really given you one way of computing the matrix for an n by n case, right? This is how you compute it. This is really important, right? This is the only way that I've given you to find the inverse, to find the determinant of an n by n matrix, and we're going to use this property. So A equals to LU, first converted into triangular matrices. So over here we'll have determinant of LU transpose, and over here we have determinant of LU. Okay, this transpose product can be written as U transpose L transpose, and this can be written as determinant of LU. Okay, now what we can do is, because this is a product, we can write it as determinant of L times determinant of U, and this is determinant of U transpose and determinant of L transpose. So again, let's sketch out what these entries would be. L had ones on the diagonal, 0 here, and some non-zeros entries here, right? U matrix was U1 to UN, non-zero matrix entries here, and 0 here. Okay, L transpose would be just the transpose of this, which means it still has, again, it's a triangular matrix. It's now an upper triangular matrix. These non-zero entries are now shifted to the other side, to the upper side, and this is 0. And U transpose is now a lower triangular matrix. It still has U1 to UN on the diagonals, non-zero entries here, and then 0 here. So what's the determinant on both sides? On the left-hand side, it's again, the determinant over here is just 1 because it's a triangular matrix, multiply all the diagonals. Over here, it's just U1 to UN, and on this side, again, this is 1, so U1 to UN. So the determinant on the left-hand side is equal to the determinant of the right-hand side. So I can put an equal to sign all around. So we see that the determinant of A transpose is equal to the determinant of A, right? And the quickest way of seeing that is, of course, again, just the way we know how to compute the determinant, just convert it into triangular matrices and then find the individual determinants and then multiply them together. Okay. So I think that's a good start into the idea of determinants, and we can now end the lecture for today. We'll continue this idea in the next lecture. All right. Have a good day. Thank you.